Everything you ever seen, every star, every planet, every galaxy, and every atom in your body shouldn't exist. That's not science fiction, that's the reality according to the laws of physics as we currently understand them. At the beginning of the universe, right after the Big Bang, energy condensed into particles. And here is the catch. It didn't just create matter, it also created antimatter, an exact mirror version of matter with opposite electric charge. For every electron, there was a positron. For every proton, there was an antiproton. And when matter and antimatter meet, they annihilate each other in a flash of pure energy. If the universe had followed this perfectly balanced equation, then, well, there would be nothing left. No stars, no galaxies, not even empty space filled with dust. And yet, here we are. Somehow, matter won. For every billion pairs of matter and antimatter particles, there was one extra matter particle left behind. Just one. But that 1 in a billion imbalance was enough to build everything. It was enough to create the universe we live in. But here is the mind-bending part. We don't know why. This imbalance, this cosmic glitch, goes against everything the standard model of particle physics tells us. It's one of the greatest unsolved mysteries in science, and it strikes at the very heart of why anything exists at all. How did we survive? Why did the universe break the rules? And what does it say about the nature of reality, when the very fact that we are here shouldn't be possible? In this video we are diving into a mystery that's bigger than the universe itself, because sometimes the most unbelievable thing about existence is that it exists at all. To understand why the universe's existence is such a paradox, we have to rewind everything, back to the very beginning. About 13.8 billion years ago, there was no space, no time, no matter, just a singularity, an incomprehensibly dense hot point where the known laws of physics break down. And then, in an instant, the universe exploded into existence, a moment we call the Big Bang. But this wasn't an explosion in space, it was an explosion of space. And within a fraction of a second, all the energy that would ever exist surged outward. Temperatures were trillions of degrees. It was chaos, pure energy stretching and expanding. As the universe cooled, the energy began to condense into particles. And here is the key moment. For every particle of matter that formed, protons, neutrons, electrons, an equal and opposite antiparticle was also formed, antimatter. It's like looking in a cosmic mirror, identical mass, opposite charge. In a perfectly symmetrical universe, that would have been the end of the story. Matter and antimatter would collide, annihilate each other, and revert to pure energy. Nothing left. No stars, no galaxies, no Earth, no you. This symmetry is so deeply embedded in the laws of physics that scientists expected the early universe to follow it exactly. But something broke the symmetry. Because when the smoke cleared, when the particles cooled and annihilation frenzy ended, there were a few extra matter particles left behind. Just one extra for every billion pairs. But that 1 in a billion imbalance, that's what you're made of. That's what the Milky Way is made of. That's what every planet, every tree, every living thing owes its existence to. It's as if the universe had a perfect equation, and somewhere along the line it made a mistake. A tiny, universe-shaping mistake. And now the question that has haunted physicists for decades is this. Why? What caused matter to win in a battle that should have ended in a draw? If this sounds mind-bending to you, hit that like button and subscribe for more cosmic mysteries. We will be covering anything from astronomy to astrophysics to wild ideas and theories. Also click the bell so you don't miss any notifications. So let's get right to the heart of the paradox. Why is there more matter than antimatter in the universe? Because according to everything we know, there shouldn't be. The laws of physics tell us that for every particle of matter created, an equal amount of antimatter should be created too. That's not a guess, it's built into the standard model of particle physics. It's how energy becomes mass. And the truth is, when matter and antimatter meet, they annihilate each other. They don't cancel out neatly, they explode releasing energy, leaving no trace of the original particles. So the early universe, if it were perfectly symmetrical, should have been a brief flash of light and then nothing. But clearly, that's not what happened. When the cosmic dust settled, matter was left standing. Not much of it, just one extra matter particle for every billion matter-antimatter pairs. But that sliver was enough to form everything we know. That's the imbalance physicists call baryon asymmetry. This isn't just a small anomaly. It's a fundamental violation of what we thought the universe should do. If matter and antimatter were truly identical except for charge, this wouldn't have happened. Somewhere, something broke the symmetry. And that something might be a crack in the standard model itself. Physicists have spent decades trying to find it. They've smashed particles together in particle accelerators, studied the decays of exotic particles like kaons and B-mesons, and searched for evidence of CP violation, a difference in how matter and antimatter behave. Let me give you a brief explanation of what CP violation is. CP violation stands for charge parity violation, and it refers to a subtle difference in the behavior of matter and antimatter. In theory, if you flipped a particle's charge, turning it into antiparticle, and mirrored its behavior, that's the parity, the laws of physics should treat both versions the same. But in certain rare particle decays, like those of kaons and B-mesons, scientists have observed that matter and antimatter don't behave exactly alike. That tiny difference, or a violation of symmetry, might help explain why matter survived the Big Bang, but the amount we've detected so far isn't nearly enough to account for the entire imbalance. It's a clue, but not the full answer. And while we found some CP violation, it's not nearly enough to explain the scale of imbalance. It's like having the answer to the puzzle, but none of the pieces fit. We know the universe favored matter, we just don't know why. And until we do, the existence of everything, stars, galaxies, and life, remains one of the most baffling scientific mysteries of all time. Let's pause and really take this in. We are talking about one of the most profound mysteries in science, the reason why anything exists at all. The fact that you're watching this video on a planet orbiting a star, in a galaxy made of atoms, all of that depends on a tiny flaw in the balance between matter and antimatter. If the laws of physics had been perfectly symmetrical at the start of the universe, matter and antimatter would have annihilated in equal measure, and the result would have been a universe filled with nothing but radiation. No stars, no galaxies, no structure, and no life. Just endless emptiness. But for some reason, matter won. Barely. And that victory is why everything exists. It's the tiniest advantage imaginable. A 1 in a billion survival rate. Yet it shaped the entire cosmos. Now, here is where it gets weird. The standard model of particle physics, our best framework for understanding fundamental forces and particles, can't fully explain this. It accounts for small differences like the CP violation observed in rare particle decays, but that effect is way too small to explain the enormous matter-antimatter asymmetry we see in the universe. So that leaves physicists with a problem. Either our current model of the universe is missing something huge, or the most important moment in the universe's history, the one that allowed matter to triumph, happened due to a mechanism we haven't discovered yet. This isn't just a technicality, it suggests there may be entire categories of physics that lie beyond what we know. Unknown particles, hidden forces, or dynamics from the early universe that defy current theories. And here is the kicker. Until we understand this, we don't really understand why we are here in the first place. It's not just a big deal, it's the biggest deal, because this tiny imbalance decided the fate of the universe. So if the standard model can't explain why matter won, what can? Physicists have proposed several theories, some grounded in cutting-edge particle physics, others venturing into wild frontier of speculative science. All of them attempt to answer one question. What broke the symmetry between matter and antimatter? One of the leading ideas involves CP violation, those rare differences in how particles and antiparticles decay. Certain particles like kaons and B-mesons have shown small signs of this, meaning nature doesn't treat matter and antimatter exactly the same. It's a start, but as was said earlier, the known CP violation is too weak to explain the overwhelming amount of matter in the universe. Another theory is called leptogenesis. Instead of starting with quarks and baryons, this idea looks at neutrinos, the tiny ghost-like particles that flood the universe. Some versions of the theory suggest that in the early universe, heavy, unstable neutrinos decayed in a way that favored matter. These hypothetical particles haven't been detected yet, but they could be a missing puzzle. Then there is the supersymmetry, a theory that proposes every known particle has a heavier superpartner. If true, this hidden layer of particles might provide new sources of CP violation or even entirely new forces that tip the scales in matter's favor. But despite decades of searching, supersymmetric particles remain elusive. Now for the wilder stuff. Some physicists have proposed that quantum fluctuations in the early universe might have randomly favored matter in one region over another, and we just happen to be in a region where matter won. That idea hints towards the multiverse hypothesis, where countless universes exist, each with different physics laws, and in most of them, matter and antimatter cancelled out completely. But we live in a one where it didn't. In all these theories, one thing is clear. Something broke the symmetry. And whatever that something is, it could redefine physics as we know it. Because behind the universe's greatest mystery might lie an entirely new chapter of reality we haven't opened yet. At some point, this stops feeling like a physics problem and starts feeling like an existential one. Because once you understand the matter-antimatter mystery, that our universe, everything we've ever known, rests on a tiny imbalance in nature, you are left with haunting question. Should we even be here? Well, think about it. If the laws of physics had played out with perfect symmetry, the universe would have ended in an instant. No stars, galaxies, and space as we know it. Just energy endlessly expanding through a void. But that didn't happen. Instead, something, whether a flaw, a force, or a freak event, gave matter the tiniest edge. And that margin of victory, 1 part in a billion, is the only reason you're able to watch this video, breathe air, or think at all. For some scientists, this sparks a sense of cosmic humility. For others, it hints at a deeper structure to the universe, one that's not random at all. Could this be evidence of fine-tuning? The idea that universe's laws are carefully set to allow life? Some take this further, invoking the anthropic principle, that we observe this kind of universe because it's the only kind that allows observers like us to exist in the first place. Then there is the multiverse idea. If countless universes exist, each with slightly different laws, then maybe it's not strange that we live in one where matter won. In all the others, no one was left to ask the question. But no matter how you slice it, the fact remains, we are here because the universe cheated. It broke its own rules in our favor. And whether you see it as a chance, design, or a sign of something deeper, it's one of the most awe-inspiring realities science has ever uncovered. We live in a universe that shouldn't exist, but it does, and that might be the most beautiful mystery of all. We began with a paradox, a universe that shouldn't exist, and yet here we are, made of matter, built from stardust, living on a tiny rock orbiting one of countless stars in the cosmos that emerged from nothing. All of it because something broke the rules. A single imbalance, one matter particle left over for every billion destroyed, tipped the scales and became the foundation of everything we know. It wasn't dramatic, it wasn't explosive, it was subtle, silent, hidden in earliest fractions of a second after time itself began. We've built particle accelerators the size of cities to chase this mystery. We've studied the decays of invisible particles, theorized new forces, new dimensions, and even new universes, all to explain why this tiny favor toward matter happened at all. But maybe the most profound part of the mystery isn't what it says about physics. Maybe it's what it says about us. That everything, life, thoughts, consciousness, come from the universe being just slightly imperfect. That creation isn't rooted in balance, but in a flaw. And if that's true, then maybe we shouldn't be searching for perfection out there. Maybe we should embrace the miracle of imbalance. Because in a cosmos where everything almost cancelled out, we are the cosmic leftovers. And somehow, that was enough. Thank you for watching, keep looking up.